Hello, this is Dr. Christy Patton-Lukes, your professor for Chemical Engineering 3111. This is Lab 8 on curve fitting. So first thing is the least squares fit of data to a straight line is the formula that we've derived, but you need to know the procedure because it's going to be very useful in fitting other types of curves. So the general formula is that you first find a set of deviations or differences, and it's the difference between your model and the actual measured value for y. So if I'm saying a straight line, y equals mx plus b, then the difference is mx plus b minus the measured y. And if I do that for all n of my data points and add them up, then I can get a sum of the errors, but some of these will be positive, some negative, so therefore I want to square them is mathematically the easiest thing to do. I could also take absolute values. But anyway, if I square these, then I get the sum of squared errors, and I want to minimize this. So the least squares means I'm minimizing the sum of the squared errors. So when I do this, I'm going to take the derivative of the error, the sum of squared errors, with respect to my parameters, in this case m and b. Set both of those equal to 0 and solve for the values of m and b that would make this the minimum. Now we could do this for any formula. Instead of y equals mx plus b, I could do it for y equals mx squared, or mx to the n power, or any function that I wanted. We also have ways of measuring the R-squared value. R-squared is a value that's going to be between 0 and 1, or it should be. The closer it is to 1, the better the curve fit. This is basically, it's used when you're trying to compare different models that might have different number of parameters. And so you can kind of look at those and see whether or not you're actually getting more value for that extra parameter that you are fitting. We have several tools that we can use within Excel. One of these is Trendline, which is probably the handiest as far as trying to figure out what's going on, but not necessarily the best if I'm trying to work with things. We have some functions we can use, slope, intercept, and RSQ, which will evaluate the slope and intercept of a straight line and the R-squared value for that line. We also have linest and logest, which are linear and logarithmic estimation tools, and these can actually do polynomials or polynomials of the natural log of your variable. And then we have the regression tool, which actually gives so much information, most of which we're not learning how to deal with in this course, but you will be looking at that when you take your statistics course. In today's activity, we're going to be analyzing Alka-Seltzer data. Now, I have done this in the labs at the school. I dropped Alka-Seltzer in water at various temperatures. The one that I have for you is on canvas that I want you to analyze. And I record the mass versus time. Now, I have to start the timer before I drop in the tablet, so you'll have to correct for time equal to 0 when we start doing measurements. And you're going to have a lot of noise to the data, so there'll be, it's not going to be totally smooth, primarily because these little gas bubbles form, they pop, a little bit of liquid goes up and then it comes back down. So you're going to have some noise in the data. Particularly for the first couple of seconds before the scale kind of lines out from me dropping the tablet in. So we'll have to disregard the very first data. I'm going to want you to estimate two variables, and I have changed this from what I have here. So what I want you to do is first look at the video for Alka-Seltzer and water and gather the data from the video. So what I want you to do is start about 5 seconds in and gather data for roughly 3 minutes. So for the first minute, record the data about every 2 seconds, and you're going to record the time and the mass. And then for the last 2 minutes, go about every 5 seconds. I found this easiest to do by just, hitting pause on the video and writing it down, typing it in, and do that. Then you're going to need to modify the data in order to get the curve fit that I'm asking you all to do. The X data is going to be the adjusted time, which simply means you're going to figure out what your starting time was and subtract that. So you're going to get an artificial 0 time based on when you started your measurement. Again, about 5 seconds in from the 0 on the timer is probably about the point where this will work best. The Y value, what I want you to do this semester is to do the mass of CO2 evolved. So in that case, what I want you to do is subtract the mass reading from your initial value of the mass, and that tells you how much CO2 has been evolved since the beginning of the experiment. And then use that Y and X and create a graph and add a trend line. So you're going to be doing a couple of different curve fits, and the first thing I want you to do is use that trend line and vary this until you think you have the most reasonable curve fit. And report that best curve fit and the R-squared value for that you did, okay, based on your data set. Ultimately, so after a while, after some other things happen, the dissolving of the tablet and some other kinds of things are happening, the reaction is a first order reaction, which means that you should have something like Y equals Kx. At the temperature I've given you, this happens about 1 minute in. So for those last 2 minutes where you were recording about every 5 seconds, you should have something that is fairly linear. I want you to find the K1 for that, okay? Then I want you to find the best possible value of K1 with its R-squared, and then look at the first 2 minutes. Now in this case, K1x minus K2x squared, it appears that there is a quadratic function, a second order function happening initially. It's related to the fact that you are having the tablet has to dissolve and there's some surface things that are happening. So for this part, you're going to need to analyze the data a little bit differently, play with the math, see if you can get it into a simple form so that you can just use the linear, or you can derive the best fit using the least squares formula. Now, you will be expected to know this for the next exam, so being able to do the derivation of the least squares formula for a simple, single parameter function is something that you ought to be able to do. Now, K1 you already know from before, okay? It's K2 that is going to be a little bit different, all right? So report your K1, your K2 with the R-squareds for each of those different data sets, and report your trend line best curve fit. Thank you very much. See you in the next experiment.